7 footnotes are all about inscribed angles. We'll start off the section with two definitions. The first, an angle whose vertex is on the circle and whose sides are chords of the circle, is called an inscribed angle. An intercepted arc is an arc whose endpoints on the sides of an inscribed angle and its other points in the interior of the angle. We actually used the term intercepted arc when we talked about central angles in our last section. In our diagram, we see an inscribed angle and its intercepted arc. The inscribed angle would be the angle ACB. So we can say angle ACB is an inscribed angle. Once again, what makes it an inscribed angle is that its vertex is on the circle itself. If the vertex is anywhere else or inside the circle, it is not an inscribed angle. So the vertex has to be on the circle itself. And then the rays would be what's called chords, two segments that cut through the circle. The arc that it creates is going to be our intercepted arc. So arc AB is an intercepted arc. So let's talk about the relationship between the intercepted arc and the inscribed angle. Our theorem states that the measure of an inscribed angle will be half of the measure of the intercepted arc. So in our diagram, the measure of angle ABC is equal to 1/2 of the measure of arc AC, the intercepted arc that it creates. We can think of this as the angle is equal to half of the arc. Another way is to rewrite this equation by solving for the arc. In doing so, you can find that the arc is double the angle. Both of these equations are actually the exact same equation. However, some students find it easier to work with two equations, one with the angle isolated and one with the arc isolated. Let's take a look at the problems. In number 1, we want to find the values of A and B, using the diagram on the right-hand side. As we look at the diagram, we notice we have a bunch of angles and arcs that are overlapping. This can be quite confusing. So a lot of times I like to highlight the arc or angle that I'm looking for and try to find its associated angle or arc that goes with it. So I'm going to go ahead and begin by highlighting the arc A. So it looks like the arc A is actually the arc PT. And if I look at this arc, I notice that it goes with the inscribed angle PQT. And I know the value of PQT. It's 60 degrees. So if I want to find A, which is the arc, it's going to be twice the angle. And you know what? Right above that, I'm going to actually write that. The arc is double the angle. Here, the arc is A, and we're going to double the angle, 60 degrees in this case. This gives us a value for A of 120 degrees. So now we know A. A lot of times when I find a variable, I like to rewrite the value of it in the diagram because it may be helpful for us in another problem. Okay, so let's go ahead now and I'll highlight another variable, in this case b. So let's go ahead, I'll highlight it with orange. So b is an inscribed angle. Looks like it is the angle PRS. And when I look at PRS, it is associated with the intercepted arc of PS or PTS. So it's this entire arc right here. So what we notice is that this entire arc angle is going to be the 120 plus the 30. So that entire arc is going to be 150 if I add them together. And since I'm looking for the angle, I know that the angle is equal to half of the intercepted arc. And I can find the inscribed angle B by doing 1/2 of the arc that we just found, 150 degrees. Multiplying those together, I get the measure of the angle B as 75 degrees. And there's my second answer for number 1. On the back page, we see a bunch of corollaries to the inscribed angle theorem. The first corollary essentially says that if you have two angles that intercept the same exact arc, then those two angles should be congruent. This kind of makes sense because, for example, if the arc was, let's say, 40, then the angle would be half of that, 20. And since the two angles go to the exact same arc, both of them would be half of the 40, or they would both be 20. So they should both match since both of them are half of the arc. Corollary 2 says that if we have an angle fit to a semicircle, that it's going to be a right angle or 90 degrees. And this should also make sense because a semicircle creates a 180 degree arc. And the inscribed angle is always half of the arc. So half of 180 is 90 degrees. Now the third corollary isn't as obvious, and it would take a little bit more explaining, which I'm not going to go too into depth about explaining corollary 3. But essentially, it can be proven that the opposite angles of any inscribed quadrilateral will be supplementary. This means that they add up to 180 degrees. So for example, in this inscribed angle, we can find that the measure of angle A plus the measure of angle C is supplementary, so that means that they add up to 180 degrees. The same can be said about angles B and D. Those would add up to 180 degrees. So these are our three corollaries that we're going to be using in the next few examples. So let's take a look. All right, problem 2, we have our first example A, where we have a diagram. Looks like we have a triangle within it and another segment within there. We also know two arc measurements. Okay, so we want to find the numbered angle. So we want to find the angle 1. So the first thing I'm going to do is actually highlight that angle so that it stands out to me visually. So here's the angle that I desire. And now I'm going to go ahead and highlight the arc that it intercepts, which would be this arc highlighted in yellow. Okay, so I see the arc and I see the angle, and actually I don't have either measure. I do have a portion of the yellow arc, 40, but I don't have the other one. But what do I notice? Well, what I notice is that this arc is actually fit to a diameter. So that means that it's going to be half of the circle, or 180 degrees. According to corollary 2, any angle fit to a semicircle will be a right angle, or 90 degrees. So that automatically tells us that the measure of angle 1 is 90 degrees by corollary 2. So I'm going to go ahead and write that in my notes as well, by corollary 2. Okay. All right, let's move on to B. In B, we want to find the angle measure for 2. So once again, I'm going to highlight the angle 2. So highlighting, here we are. There's the inscribed angle that I want, and it goes with this unmarked arc, once again, that I don't know. It's not a semicircle, so I can't say it's a right angle, so I have to look for something else. Well, what I do notice is that this yellow arc also goes with the 38-degree angle. So that means that both angle 2 and the 38-degree angle are fit to the exact same arc. If the same two angles fit to the same arc, that means that those two angles must be congruent. So that means that the measure of arc 2 or angle 2 has to be the same as the 38-degree angle, and therefore the measure of angle 2 is equal to 38 degrees. That is corollary 1. Okay, let's take a look at our last example, but the most complicated example, because we have 4 angles to find. We have angles 1, 2, 3, and 4. So if I highlight angle 1, right away I notice that angle 1 is fit to a diameter or fit to a semicircle. So that means that angle 1 is automatically going to be 90 degrees. Now, either by corollary 3 or corollary 2 again, you can draw the same conclusion about 3. Because 3 is also fit to a semicircle, that would be corollary 2, or you could actually use the fact that angles directly across from each other in a quadrilateral will be supplementary, and 90 degrees is supplementary to another 90-degree angle. All right, I'm going to go ahead and erase the highlighting in this particular picture so that doesn't look too confusing. And I'm going to list the fact that we noted that measure of angle 3 was also 90 degrees, again by corollary 2. And I'm going to put those in our picture, 90. Okay, so let's go ahead and look at angle 2. So if I highlight angle 2, and I'll do it in yellow again, it goes with this arc over here. And unfortunately, I don't know either arc or angle measurement. So how could I determine that? Well, I could try to find if there's a way that I could find one of the other arcs, or maybe I can turn to angle 4, which I think I'm going to do at this time. I'm going to turn to angle 4 and see if this one's easier. If not, then I'll have to solve one of them. So let's highlight angle 4 in orange. Angle 4 actually goes with the arc that I'm highlighting in orange, which, while I don't know the total right now, I have both parts, so I can find the entire arc by just adding them together. So the entire arc measurement here is going to be the 60 plus the 80, or 140 degrees. So to find the angle for 4, this is an inscribed angle. The angle will be equal to half of the arc. And I can just go back to the theorem for inscribed angles. So that means that the measure of angle 4 is equal to half of the 140. Or in other words, it's going to be 70 degrees. And this is actually just the inscribed angle theorem. Okay. All right, so now we have 1, 3, and 4. So now let's see if that will help us with angle 2. So let's fill in 70 degrees for angle 4. Well, because this is a quadrilateral, an inscribed quadrilateral more specifically, angle 2 is directly across from our 70-degree angle, so that means that angle 2 should be supplementary to angle 7. So angle 2 will be equal to 180 degrees, take away the 70-degree angle that we already have, or in other words, 110 degrees. We used corollary 3 here in this part of the example. And there's inscribed angles and their relationships to their intercepted arcs.